Hi everyone, thank you for coming to my virtual talk. I'm Dan Van Beveren, a student at Haverford College working with Professor Walter Smith. Charge transport mechanisms in DNA have attracted significant attention recently, given the molecule's unique potential for use in nanocircuitry as a monomolecular wire. Briefly, charge transport in DNA strands is thought to be dominated by three different mechanisms, which are highly dependent on the base pair sequence. Guanine cytosine bases have a relatively low electron affinity, making it relatively easy for an electron to hop from one GC base to an adjacent one, assisted by thermal energy. Adenine-thymine base pairs have a higher electron affinity, and so it's very difficult to remove an electron from one and send it to a neighbor. Hence, it's energetically favorable for an electron to move from GC bases to GC bases by tunneling through an intervening AT base. Since the probability of tunneling through a barrier decreases exponentially as the barrier grows longer, tunneling isn't viable for blocks of AT bases more than 2 or 3 pairs long. In that regime, extended thermal hopping or domain hopping, in which an electron is delocalized over a longer stretch, becomes the preferred mechanism. This general picture of DNA conductivity has been largely verified recently using STM break junction methods, in which a single short DNA strand is trapped between an STM tip and an electrode, and then a current is run across and a voltage measured. This technique has led to exceptionally reproducible results, but so far has only really been applied to DNA strands measuring about 20 base pairs long. Measuring longer molecules is more difficult, and one of the more promising methods for doing so involves depositing DNA strands on lithographed electrodes on top of an insulating substrate. Measurements with this method have not been as clean or reproducible, but offer the advantage of first allowing longer molecules to be measured, and in the long run, being more easily integrated into more complicated circuit elements. Since this measurement technique generally doesn't return very conductive values for DNA. It's thought to be an insulator with resistances per strand on the order of teraohms. We have sought to address this lack of conductivity by exploring the properties of DNA-Porphyrin hybrids. Specifically, we have looked at the intercalation of TMPYP in the base pair stack of these DNA strands. TMPYP can bind to DNA strands in multiple different ways, whether externally binding with interactions between molecules or a more spread out binding, but we're really only interested in the intercalation, as that would allow for electrical interactions between the porphyrins and the base pairs where the conduction is expected to happen. So to verify that this intercalated and didn't bind in one of the other modes, we used UV vis spectroscopy, which previous studies have shown returns a redshift and hypochromism in a DNA porphyrin solution when the intercalation is successful. This is the results shown, and we observed such a hypochromism, which again confirms successful intercalation of the porphyrin molecules. To actually execute our experiment, we used lithographed electrode pads with interdigitated fingers. DNA strands were deposited laying across them. The side view is shown here. We, for part of our experiment, illuminated it from above with a laser. To actually deposit the DNA strands, we mixed them in solution with the porphyrin to allow intercalation, then added a buffer solution and magnesium chloride. The magnesium chloride is present to provide positive ions to facilitate binding, or rather adhesion, between the negatively charged DNA backbone and the silicon dioxide substrate. So these are AFM images that we produced with one of our samples, shows clearly the DNA strand spanning the distance between the electrodes. Slightly larger view shows that this pattern is relatively uniform and can be seen across a larger area. When we applied a constant voltage, 2 volts, across this sample and illuminated it with a laser, we found that at low humidities there was very little effect. The data shown here shows no significant change in current when the sample is illuminated with a laser. at 2% relative humidity. Similarly, at 45% relative humidity, the laser showed no significant effects. There was a much more noticeable change in conductivity once we got up to 62% relative humidity, again with 2 volts applied across and illumination from a 2 kilowatt per meter squared laser. There was a significant increase in the conductivity when the laser was turned on. This was yet more pronounced when the humidity was increased to 71% and the same laser illumination was applied. We ran a few control experiments to verify that this behavior really was unique to the DNA-Porphyrin complexes. The first experiment simply had plain DNA laid across the electrodes without the porphyrin intercalated. This was at 80% humidity. The results seen on the left shows that there's no significant change in conductivity with the laser. The second experiment, we used the deposition solution with the porphyrins and magnesium chloride, but with no DNA present, to rule out the possibility that the photoconductivity was due to rogue porphyrins left on the substrate. As in the first case, there's no significant conductivity, and the laser does not change it much at all either. We tracked the changes in the conductivity as a function of humidity throughout a long period over which the experiment was repeated multiple times. Generally, we increased the humidity from a low value to up to about 71% over the first 10 days, waited for a while, and then decreased it back to 0. The dark current shown here is defined as the current without the laser turned on, and the clear trend is that the dark current increases with increasing humidity. However, there seems to be some kind of hysteresis here in that the conductivity is higher for a given humidity when we're in the decreasing section of this run. So it seems that the exposure to a high humidity leads to some persistent effects. And similar was seen in the photocurrent, which we define as the increase in current when the sample was illuminated. Again, the effects of humidity seem persistent. You can see that the second half of this experiment shows generally higher conductivities at a given humidity than the first half. And there is no significant photoconductivity for low humidities on the first increasing ramp. In conclusions, we generally see that DNA-Porphyrin complexes exhibit photoconductivity and dark conductivity over distances of at least 400 nanometers, and our controls show that this is almost certainly due to the DNA-Porphyrin complexes and not some other qualities of the DNA or the solutions in which they were deposited. Also interesting is that the photoconductivity is persistent with no significant photoconductivity at low humidity. This is an interesting result in that the changes are not expected to be quite as persistent as observed. It's been theorized that the presence of humidity will hydrate DNA molecules, which will first alter the electronic structure and second alter the physical structure. Both would be expected to lead to a higher conductivity, but that should be a more reversible change than we're seeing here. And so it's very possible that it's not simply a structural change being caused by the humidity, but an electrochemical change that takes a longer time to reverse. We also notice that the photoconductivity, like the dark conductivity, increases with the humidity exposure duration. And again, there's a persistent effect from the humidity. Thank you. That just about sums it up. Lastly, I'd like to thank our collaborators and funding sources and you for sitting through this talk, and just say that if you have any questions, please feel free to use the comment section.